Do the water controllers in your plant look like this, or even this? Then stick around and watch this webinar to find out exactly how to tune them. Hello, I'm Luke Evans. I'm a Senior Process Engineer at MyPack. This webinar will cover approach for site engineers or site metallurgists on how to tune a flow controller, specifically a proportional and integral controller for water addition. If your flow loops aren't up to scratch or look anything like those previous trends you just saw, then stick around as this webinar will help you investigate and tune your water loops for better performance. First off, why should we control water in our plant? Typically, you are adding water or controlling water in your process for a pretty specific process objective. This could be controlling density, maintaining a level, for heat exchange purposes like copper blocks in a smelting environment, or adding wash water. And there's plenty of other reasons why you want to control water. Now, if those water loops aren't tuned very well, you might struggle to meet the process objective, which could lead to poor grinding performance or poor separation in your cyclones if you're not controlling density well. It could lead to quite a lot of mess and even equipment damage if you don't maintain that level. It could lead to safety incidents or some major downtime if your heat exchange system is not controlling correctly. And it could lead to grade and recovery loss if your wash water isn't tightly tuned on your cleaning circuit. There are plenty of other examples of this, but the point is, a simple flow loop that might be overlooked could be causing you heaps of heartache without you really fully realizing it. So, what's involved? A typical water flow arrangement probably involves a pipeline, a flow instrument, some valving, and an actuator on a control valve. From a control perspective, the PV coming from the flow instrument is coming back to the flow controller located in your control system. The set point that you're trying to control the flow to is entered by the operator or comes from another controller. And the controller output or the manipulated variable signal goes back to the valve actuator, which then changes the valve position to control the flow. Pretty simple, to be honest, which is why it's overlooked. The loop must be designed to deal with installed valve characteristics, any changes in your upstream or downstream pressure through this line, regular set point changes, and any signal noise coming from the flow meter. Now, to improve the control performance of this system, we need to be able to access a few levels of automation. Which brings us to the 3 layers of the automation pyramid. In this instance, we'll be dealing with the bottom 3 layers, the instrument layer, the control layer, and the supervisory layer. This first instrument layer is where all your physical hardware sits. It measures the process and provides all the information up to the control level. This second layer is where your control logic sits in the PLC or your DCS, depending on how your system is set up. And then the final third layer is the supervisory layer, where you can trend and monitor the data of the PID controller and derive its performance. So, where do we start? That's right, the first level, the field, where all the instrumentation and hardware sits. So you need to go out in the field and inspect what you've got. You need 2 feet and a heartbeat. So grab your P&ID drawing and go for a walk in the plant. First of all, you need to have a look at what's installed. Is what's in front of you the same as what was originally designed? And check it against your P&ID drawing. Second, check your control valve. Is it able to fully travel? Can it go from 0 to 100% without any dramas? Does your flow meter have any erratic readings or any errors on the transmitter display? Are the valve air connections leaking? Are your flow meter cables connected? Are they sealed? Are they in good condition and fixed in place? Or are they just flapping about the place, causing lots of problems? And finally, does the control valve make any large, irregular movements when it's in automatic? If this seems to tick all the boxes, it's then time to move on to a point-to-point control test. So call up your control room operator and ask to see what the value of the flow meter is in the control system, and check if that value matches what you're looking at in the field. Then ask them to put the controller into manual and do a step test on the valve position from wherever it is currently up 10%. Let the flow even out and then drop it back to where it was originally. After that's successful, flick the controller back into auto and watch the valve position and see if any erratic movement continues or if the valve jitters. As you can see here, this flow meter is reading rather erratically, going from -7 all the way up to about 30 meters cubed an hour. So if you see something like this, probably investigate further before doing any tuning. Which leads us on to step 2. So here's a typical trend of a set point change made by the water controller that we're trying to improve. Now, these parameters, we've got two trends. We've got the flow in green as a set point and the flow in red as the present value from the flow meter. That's the top graph. And in the bottom graph, we've got two trends for the valve position. The black trend is a feedback from the valve actuator back to the control system, defining its actual position. And the red trend is the output of the controller to the valve. Now, these are two very different trends, and your system might not be set up this way. You might not have valve feedback. You might just have controller output as your MV. But for the purposes of this webinar, we've set this up to be able to show the differences in valve position and how it can affect your controller. So looking at this trend specifically, we can see two major issues. The first problem is that the controller has quite a lot of gain, i.e. its proportional term or P value is quite high, which is causing a lot of unnecessary oscillation even when it's sitting at set point, which is caused by the excessive valve movement. Now, that excessive valve movement is the controller responding to the instrument noise, and because of the high gain, the error is constantly being reapplied to the controller excessively and doesn't need to happen, which is causing the valve to jitter, which is making the PV move even further and oscillate further around the set point. You can sort of see here that on a set point change, we've got some variation and then it evens out again and then gets worse. And this is pretty typical of a over-tuned, very aggressive P turn. So now let's look at our manual step test for when we put the controller in manual and step the valve position up 10%. Zooming in, you need to identify the timestamps of when you made that step test and the values of your PV before and after. So in this instance, we made the step test at roughly 73 seconds, and it started at 4.54 liters a second and went up to about 5.64 liters a second at about 93 seconds. And this was caused by a 10% MV shift. Now, this 10% MV caused that process response of about 1.1 liters per second. Now, specifically in this type of process, this is a self-regulating process. So the MV step caused a PV change, which eventually settled out to a new limit. Now, once we've got those points, the MV percentages, the PV liters per second, and the timestamps, write them down because you're going to need them to calculate the PID control settings. So today we're going to use the Lambda method for self-regulating processes. We're simply applying this formula here, and we need to calculate each individual parameter from the step test information that we just captured. In particular, we need the process gain, or the GP value, as well as the tau, or the time constant value. So from this nice, smooth example graph, we can determine how to acquire them. So the GP value is the delta P over the delta MV as a percentage. So the delta PV needs to be a percentage of the full span of the variable that we're using, not just the difference in the engineering flow units, which I'll show in a working example of shortly. For the tau value, you need to identify the point that the process is fully settled or almost fully settled. With instrument noise, this can be a bit of metallurgy magic, so take your best guess. I like to use the 4 tau point, which is roughly 97% settled, because waiting for the process to fully settle isn't always practical. So for me, we're going to be using tau is the settling time divided by 4. I'm going to be using a lambda value of 1 because I want an aggressive control response, and tau d is a dead time, which for this system will be 0. Dead time is the difference between your MV shift and your process response. So here you can see there's a small dead time in the example, but for a flow controller where your control valve should only be a few meters from your flow meter, you shouldn't see any dead time. If you are seeing a lot of dead time, there's either something wrong with your hardware, or you could be doing something with the signal in your control system, which we'll cover later. Now, the worked example. So we're going to take the 5.64 liters per second minus the 4.54 liters a second, which is our delta in our PV, and we're going to divide that by the full range of that flow from 0 to 100% valve opening, which conveniently is 10 liters a second. We're going to take that term and divide it by the difference in the MV, 60 minus 50, giving us a total GP of 1.1. So it's important to note that that 10 liters a second converts the engineering flow units back to a percentage. Moving on, we're now going to find the tau value, which is identifying the settling time. And for me, it's the difference between 87 seconds and 73 seconds. Now, I'm using 87 seconds because the settling time of 97 seconds is a little bit too far gone. And due to the instrument noise, the exact point of trying to figure out where the process is settling can be a bit vague. So I've stuck with 87 seconds because you can verify this against the valve position. And 97 seconds is definitely far too gone. At the end of the day, pinpointing your settling time to an exact point in time isn't necessary because you're going to end up iterating the tuning parameters a little bit when you go to tune the loop. So tau CL is then 3.5 as well because we're using a lambda value of 1. Bringing that all together, we get a G value or a process gain of 0.91 and an integral term of 3.5 seconds. Please note, these numbers will not be the same for you. If you have exactly the same numbers as me, that means our systems are identical, which is probably impossible. So you will yield different results. Make sure you're correcting your flow range by correcting your delta PV by the full range of the flow of your system. So we've got our new PI terms for our controller, 0.91 and 3.5 seconds. What about derivative? Well, it's rarely seen in metallurgical processing. It's not really required for a simple flow controller. You generally see differential terms used in second order exponential systems or ramping process types. but you rarely see them in a self-regulating process like a flow control. If you are using a derivative term for your water flow controller currently, maybe try turning it off and applying these new settings that you've just calculated. So, how do you change the settings of a PID controller? This is where systems engineers and metallurgists share a common phrase. It depends. Unfortunately, I don't have enough time to go through every single control system that exists and the variety of different ways that you can change P&I terms and the various UIs that allow you to do this, which leads us to step 4. Before any tuning can begin, it's probably a good time to have a chat with your friendly control system engineer or whoever owns your control system on site, be it electrical or systems engineering or even IT. To make the tuning go smoothly, it will be a good idea to understand what form your PID controller is in. You could ask what units the integral term is in, and this could also give a good indication of what the form is. Basically, there's two forms, the independent structure and the dependent structure. In the independent structure, each P, I, and D term is individual from each other, whereas in the dependent structure, the I and D terms depend on the proportional gain. So, if you find out the units of your integral, if they're in minutes or seconds or any kind of time engineering unit, you're probably in the dependent structure. If it's 1 divided by time, you're in the independent form. The independent form could also be referred to as the integral gain or the Ki value, and the dependent form, which could be in seconds, milliseconds, or even minutes, can also be referred to as seconds per repeat, the time taken to repeat the gain, the integral time, or the reset time. For the purposes of this demonstration, we're going to be using the dependent form. Once you know your form, it's probably then best to check all the other logic within the system and the specific settings of your PID block. So you might want to review your control system manual if it's available to help you identify any sneaky calculations that might be going on that you're not aware of. If all's looking good, then it's time to plan on when you're going to make the changes and inform your operations team of that plan and follow your site's change management procedures. Testing our new settings. So, if your control system or SCADA package is designed well, you should have a controller faceplate available to you that should allow for you to update these settings within the controller. If not, you might need to go back to your control system owner, as you might need to go deeper into the control logic specifically to find out where you can actually change the settings. They might be able to create a faceplate for you so you can do it straight from the control room HMI. Now, depending on the system, you might also need to take the controller out of auto and operate it in manual to allow for the changes in settings to take effect. Now, the values we calculated earlier, a value of 0.91 for proportional and an integral value of 3.5 seconds, these are just a good starting point. So once you've put them in, it's time to stress test. So I've updated them into the controller here and made a couple of set point changes with my system. So the P setting's 0.91 and the I setting's 3.5, and the response is fairly reasonable. Once you've stepped it up and down in auto, sit down and observe the new performance and remember back to your original process objectives. Does this controller need to be tuned for load response due to variations upstream, or does it need to have good set point response? For me, this flow controller is a slave loop for density control, so I need it to have very good set point response. I'm pretty happy with these settings, but let's try and iterate and see if we can improve them. So the process in doing this is just slightly changing your P term or your I term and then seeing how it responds when you make set point changes. So here's the results of that. Here I changed the proportional term to 2.0 And here I change the integral term all the way up to 10 seconds. Now, on the integral of 2.0, you can see that the process response is much more aggressive. And then on the integral term of 10 seconds, it's quite slow and it's barely getting to its set point before we're making another change. So I'm not happy with the integral term. Let's just look at these two graphs in more definition. So taking a deeper look at these two, we need to pay attention to what the valve position is doing. We can see on the left, using our initial calculated settings, the valve position in responding to the output of the controller is relatively smooth. Whereas on the right, the valve response is a little bit jittery. This higher gain is causing this controller output to make the valve jitter, especially when it's already sitting at set point, which will cause excessive wear on your valve, which is not sustainable for this system. So we're going to stick with the original calculated settings. You might not find that. You might find a happy medium between your iterated proportional and integral terms versus what you originally calculated. At the end of the day, just choose the one that suits your process in the best way. Now, I have two more tips that might help you in resolving tuning issues. The first is to consider a filter block or a lag block. As you can see in this example, the instrument noise is excessive, and no matter of PID tuning is going to help you resolve this problem. If you can't remove the noise in the signal from the field, you could consider a lag block on the PV signal prior to that signal entering the PID block. When doing this, you need to consider the effects of adding the lag to the PV signal. Essentially, this lag block is trying to dampen out the varying instrument signal and present a more consistent, reliable PV value for the PID function block to then run its calculations on. Inherently, though, this lag block will add a delay, not exactly a uniform delay, but some form of delay in this PV signal, which will essentially slow the controller's response. Due to that, an effective lag setting, a parameter that you put into the lag block, is highly dependent on your integral term. A rule of thumb is to typically divide your integral term by 5 and use that value as your lag setting. For this flow controller, we have a pretty low integral term, so the instrument noise frequency would need to be excessively high to kind of consider a lag block to be effective, because we're reapplying the gain so quickly. So at the end of the day, if the noise is quite high, maybe you want to resolve the cause of that noise by investigating the hardware in the field first, as opposed to masking the problem with a lag block in the control system. Just some food for thought. Which leads us to the second thing. You could consider the deadband and the resolution of your valve actuators. So to reduce wear on valves, due to many reasons that we've already covered, actuators are often installed with a deadband or a resolution setting in the actuator themselves. The graph on the left here is a great example from that, which has been provided by Emerson. It shows the effects of different resolution actuators and their response to the control inputs and the effect on the flow rate that's being controlled. So in the top graph, we have a very fine resolution on the actuator, and in the bottom graph, it's quite a coarse resolution or a large deadband of about 10% versus 0.5%. So you can sort of see here, when we make an input signal change of 0.5 and 1%, you can see on the blue line that the actuator is moving and the flow is responding accordingly. Whereas with the larger deadband or the coarser resolution on the actuator, you don't see any flow response and the actuator isn't moving to these more finer movements. Now, similarly on this second graph, Improving that resolution can allow for your MV to finally settle in its required position to control the process. And you can see a good example of that here. Here, the valve's trying to find 40%, but can never actually get there due to the resolution settings. And then after changing, it finally flattens out. To summarize today, we've done 5 straightforward steps for any site metallurgist or engineer to tune the PI settings of a water flow controller. First off, you need to get out into the plant and inspect the process and your instrumentation in the field. Once you've verified that everything seems to be working correctly, conduct some manual step tests and trend the results. From those step tests, calculate your new controller PI settings, and today we use the Lambda method. There are many other methods out there. Once you're satisfied with those settings, it's time to consult the control system engineer or whoever owns your control system just to double check all the logic going on in the background associated with the controller that you're trying to tune. Once everything is satisfactory, talk to your operations teams and follow change management procedures before going and changing any of your controller settings. Once you're ready, test the new settings and then iterate from there, changing your proportional and integral term just a little bit to suit your process dynamics. If you'd like to see any more of these webinars on any type of loop, feel free to leave a comment or reach out to us on your website. If you'd like to participate in our 2-day loop tuning course, feel free to reach out as well. If you need any instrumentation, process, or control system engineering services, contact sales@mypac.com.au. Bye for now, and see you in the next one.
Free audio post-production by alphonic.com.